Every line of code you write, every feature you build, holds the potential for something unexpected, a new bug, a subtle regression. In the fast-paced world of software development, this uncertainty can slow you down, make you hesitant to refactor, or even worse, lead to critical failures in production. For short-term projects or quick fixes, manual testing might seem sufficient. But what about applications built for the long haul? What about systems that need to scale, evolve, and remain stable for years? Relying solely on manual checks becomes a time sink, a bottleneck, and a constant source of stress. That's where automated testing comes in. It's not just a best practice, it's an investment in reliability, maintainability, and ultimately, your peace of mind. Automated tests act as a safety net, diligently checking your application's logic, catching regressions, and ensuring your code does exactly what it's supposed to. Today, we, at SystemsDK, want to guide you through a powerful, yet simple, way for building truly robust applications. We'll explore a three-level approach to automated testing. This methodology, widely adopted and proven, will empower you to write more stable code, deliver with confidence, and make scaling your projects a breeze. So, you're ready to start automated testing, but you immediately hit your first major question. What types of tests should you even write? If you use Symfony framework, you look at the official Symfony documentation, and it clearly defines three types: unit tests, integration tests, and application tests, which they also call functional tests. But when you use Laravel framework, you jump over to the Laravel documentation, and suddenly, there are only two types by default: unit tests and feature tests. This can be confusing while switching from one framework to another. Is a feature test just a different name for an application test? Why does one framework recommend 3 levels and the other only 2 by default? If you've learned a different approach, it's not wrong, just different. So, which standard should you choose? Let's clear this up right now. We, at SystemsDK, believe in clarity and building on proven standards. First, to answer the main question, yes, for all practical purposes, a feature test in Laravel is the same as an application test in Symfony. Both are designed to test a full HTTP request cycle from the outside in. We strongly propose adopting the 3-level approach as a clear standard for any modern PHP application. This model, using unit, integration, and application tests, gives us the clearest separation of concerns and will cover almost every case you'll encounter. So, let's quickly define these 3 types so we're all on the same page. First, at the bottom, are unit tests. A unit test is simple. It checks a single unit of code, like one class or one method, in complete isolation. It uses mocks to fake all external dependencies like databases or APIs. The main goal? To be extremely fast, allowing you to run thousands of them in seconds. Next, in the middle, are integration tests. As the name implies, these tests check how multiple units integrate with each other. A common example is testing if your user service can actually write to the service container or a real test database. They are slower, but they verify the wiring between your classes. Finally, at the top are application tests, also known as functional tests in Symfony or feature tests in Laravel. These are the most powerful. They simulate a real user action, like making an HTTP request to your API, post, API our user, and checking the full response and database state. They test the entire application stack working together. So now we have our 3 standardized tools: unit, integration, and application tests. But this leads to the most important question of all, the one that defines your entire workflow. In what order should you write them to be the most effective and save the most time? And that is where our strategy comes in. So, we now have our 3 standardized types: unit, integration, and application tests, and this brings us to the most important strategic question: in what order should we write them for maximum effectiveness? Now, the classic approach to testing, and particularly to test-driven development, TDD, is the bottom-up strategy. You start at the very foundation of the testing pyramid. This means you first focus on writing numerous isolated unit tests for every single class and method. Only once those are solid do you then move on to integration tests to verify how your components interact. And finally, you write a few large application tests to ensure the entire system works as a whole. Let's be clear, this is a fantastic, fundamental approach. It's excellent for learning, it enforces meticulous design, and it builds your application from a foundation of perfectly functioning, isolated bricks. It undeniably guarantees quality at the lowest, most granular level. But in our years of experience at SystemsDK, building complex, real-world business applications for clients, we've found that while the bottom-up approach is robust, it isn't always the most efficient for real-world project delivery. Why? Because you can easily spend an hour crafting 5 perfect unit tests for a few simple services, only to find that one application test covers 90% of that same logic in 10 minutes. This often leads to writing tests you don't actually need, consuming valuable development time. That's why we prefer a more pragmatic and business-focused strategy, often called the top-down or outside-in approach. We start by testing what the business actually cares about, the user's journey and the core features. Step 1, we start with the application test. We first write a test that simulates a real-world request. For example, making a POST request to our user registration API endpoint, API v1 user. We assert that we receive a 201 created response and that the new user is correctly persisted in the database. This single application test immediately validates the entire business flow, from the route handling to the controller, through the service layer, and finally, to database persistence. It ensures your core feature works as expected. Step 2. We run code coverage analysis. After our initial application test, we use a coverage report like a map. This single test might already cover 80% or even 90% of our new feature. The report highlights the blind spots, the specific if statements, complex decision trees, or edge case error conditions that our application test didn't explicitly hit. Step 3. We write targeted integration and unit tests. Now, instead of blindly testing everything, we write tests only for those uncovered red areas. If our application test missed a specific validation for a duplicate email error, we write a targeted integration test to specifically verify that error condition. Similarly, if the coverage report shows that a highly complex price calculator service wasn't fully exercised by our top-level tests, now we write a fast, isolated unit test to precisely check its intricate mathematical logic. This top-down strategy, combined with smart use of code coverage, ensures that 1. You always start by validating the real business value of your feature. 2. You do not write unnecessary tests, which saves significant development time and reduces maintenance overhead. And 3. You still achieve robust, multi-level test coverage, using unit and integration tests as a surgical tool to fill precise gaps, rather than a blunt instrument to test every single line of code from scratch. This might sound great in theory, but let's see how it works in practice. In the next chapter, we'll open our Docker Symfony API repository and apply this top-down methodology to write our first application test. In the previous chapter, we laid out the theory behind our efficient, top-down testing strategy. Now, let's bring that theory to life by diving directly into the code of our Docker Symfony API boilerplate project. For our practical demonstration, we'll focus on a very common and essential API endpoint, creating a new API key. This functionality is typically handled via a POST request to API v1 API key. It's an excellent example because it requires a full round trip through our application to be successfully executed. Following our top-down approach, our very first step is to write an application test. You'll find it within our project structure at tests-application API key transport controller API v1 API key controller test.php. This test is designed to simulate a real-world interaction, either from a user or another client application. Inside, you'll see we use Symfony's built-in HTTP client to make a POST request to our chosen endpoint. We send along any necessary data, configured exactly as a real client would interact with our API. Our primary assertion in this application test is to check the HTTP status code. For a successful creation of a new resource, we expect a 201 created status. This single check immediately tells us if the core API contract is being met. Next, we meticulously validate the JSON response body. We ensure that the API returns all the expected data, such as the newly generated API token, and that it's formatted correctly and not empty. This confirms the data flow out of our application, and critically, we then verify the database state. After the request has been processed, we directly check if the new API token has been correctly persisted in our database. This final step provides comprehensive assurance that all layers of our application, from routing to the controller, through the service layer, and down to the ORM, worked harmoniously and correctly. This single application test, designed to validate the entire creation of an API key, serves as our first and most comprehensive safety net. It effectively validates the entire business process from end to end, mimicking how a real user or client would experience this feature. Let's run this test to see it in action. As you can observe, it passes successfully. With just this one comprehensive test, we validated the core functionality of our API key creation endpoint, proving that the feature works as expected. Our high-level application test is passing, which is a great start. But remember our top-down strategy. We don't just trust the happy path, we use code coverage analysis as our map to find what we missed. Looking at the coverage report for our internal open SSL crypt API key service, you can clearly see red flags. Our application test didn't trigger two critical edge cases. First, the token length validation during encryption, row 31, and second, the validation checks during decryption, row 51. These are internal logic branches that are difficult to target precisely with an external HTTP request. So, to surgically cover these gaps, we write an integration test. You can find it in tests, integration, API key, application, service, crypt, OpenSSL, crypt API key, service, test.php. By extending Symfony's kernel test case, we boot the actual application kernel and get the real service with its real dependencies directly from the container. Here, we can specifically target those uncovered scenarios directly. We write test cases that deliberately pass tokens with invalid lengths or missing parameters directly into the service methods. We then assert that the service handles these invalid inputs correctly, usually by just returning early without performing any action, exactly as those uncovered if statements dictate. By running this targeted integration test, we've ensured that our internal service handles these edge cases correctly within the real application context. And if we were to run the coverage report again, those red lines would now be green, confirming our strategy worked. Now our services are integrated correctly. But what about catastrophic failures at the lowest level? For example, what if the underlying cryptography service is entirely missing its encryption key configuration? To test this kind of fundamental robustness in complete isolation, without even booting the framework, we need unit tests. Let's look at that in the next chapter. Our application test covers the happy path, and our integration tests cover internal edge cases. But what about fundamental catastrophic failures at the absolute lowest level? For example, what if our cryptography service is configured with a completely unsupported algorithm? This isn't an edge case, it's a broken service that should fail immediately and loudly. To test this kind of robustness in complete isolation, we use a unit test. You can find it in tests, unit tool, domain, service, crypt, OpenSSL crypt service, test.php. Notice that this class extends PHP unit's generic test case, not Symfony's kernel test case. We are not booting the framework here, we are testing the OpenSSL crypt service purely as a standalone PHP object. Look at the first test. We instantiate the service, but we deliberately pass a completely nonsensical string, Mickey Mouse, as the encryption algorithm. We are simulating a fundamentally broken configuration. We then assert that calling encrypt immediately throws an exception, proving the service fails safely without ever trying to run invalid crypto operations. We do the same thing for decryption, ensuring it fails loudly if required parameters, like an IV or tag, are missing. These unit tests run instantly, confirming our base level robustness. And finally, if we run our full coverage report one last time, we see a beautiful sea of green. By following our top-down strategy, application first, then targeted integration, and finally isolated unit tests, we have achieved complete, meaningful coverage efficiently without wasting time on redundant tests. To summarize, don't just write tests, have a strategy. By adopting this pragmatic top-down approach, you ensure you are testing the real business value first, saving significant development time and avoiding redundant work. You can find the complete source code used in this video in our open source GitHub repository. The link is in the description below. If you found these practical examples helpful, please consider starring the repository on GitHub and subscribing to the channel for more robust engineering strategies.